Hello, students. My name is Sumit Sagar Hota. I am a PMRA PhD scholar, IIT Palakkad. This is the summary section of the course, The Turbulent Combustion Theory and Modeling by Professor Ashok Desar by NPTEL. Okay, in this section, we will see some of the important questions from different lectures and we discuss them. Now, in this section, the questions are from both the prescribed textbook and Introduction to Combustion Concept and Application 3rd edition 2017 McGill, as well as it is also from the website www.sandfoundry.com. Okay, in this section the questions I already solved and I will only go through the questions, and at last one or two questions I will only solve from the last lectures, so that it will be somewhat beneficial for you. And last questions, two questions are from the lecture 12. So that are most important questions. Okay, so first we go to the some simple questions. This here 25 written, it means it's question number, chapter number 25, sorry, chapter number 2 and question number 25. Okay, lecture 1 to 5 means it's cover chapter number 2. Okay, chapter number 2. Okay, you can see in the question, the lower heating value of a methane is 50,016 kilojoule per kg. Determine the heating value per mass of the mixture, per mole of the air fuel mixture, per cubic meter of the air fuel mixture. Okay, so now you can see I just write down what are the things given, then I write down what are the things to find out. Okay, which is LHV of kilojoule per kg of the mixture and kilojoule per kilomole of the mixture. Okay, and kilojoule per meter cube of the mixture. These are things to be find out. Okay, now you see I just write down the equation of the methane combustion. Okay, that is CH4 plus A times O2 plus 3.76 times N2 gives rise to CO2 plus 2H2O plus 3.76 A N2. For phi equal to 1, A is equal to x plus y by 4, and where y equal to 4 by 4, which is equal to A equal to 2. Okay, so what is the air fuel ratio? The air fuel ratio comes out to be 4.76 A into molecular weight of the air divided by molecular weight of the fuel. Okay, and the values comes out to be 17.12 kg of air divided by kg of CH4. So now we just find out the F divided by A plus F of mass. Okay, and the value comes out to be 1 plus, okay, we just have to rearrange the equation again. Okay, so the when you solve this thing, it comes out to be 1 by 1 plus 17.12 kg of fuel divided by kg of the mixture. Okay, so now we can substitute in the formula of LHB, lower heating value, for kilojoule per kg of mixture. Okay, and by substituting, that is LHB in kilojoule per kg of fuel into 1 by 1 plus air fuel ratio. Okay, so kg of fuel get cancelled. Okay, and the value comes out to be 2760 kilojoule per kg of mixture. Now let's go to our second bit, which is kilojoule per kilomole of the mixture. Okay, so now you see, first we have to find out the air fuel ratio on molar basis. Okay, which is equal to 4.76 times A is equal to 4.76 into 2, and the value comes out to be 9.52 kilomole of air by kilomole of fuel. Similarly, as the previous procedure, we can find out the value of F divided by A plus A of molar, and we can rearrange it as 1 by 1 plus air fuel ratio in molar basis, and the unit should be kilomole of fuel divided by kilomole of the mixture, and the final answer should be 1 by 1 plus 9.52 kilomole of the fuel divided by kilomole of the mixture. Okay. Now we just have to find out LHV for kilojoule per kilomole of mixture. So we have already LHV kilojoule per kg of the fuel, and we know also the molecular weight of the fuel. Okay, and we also know 1 by 1 plus air fuel ratio. Okay, just to multiply these things, then the kg of fuel and kg of fuel get cancelled, and kilomole of fuel and kilomole of fuel get cancelled. Now just substitute all the values, that is LHV kilojoule per kg of fuel is 50,016, and molecular weight of the fuel is 16.043, and air fuel ratio is 1 by 1 plus 9.52. And when you rearrange all these things, you get the value of LHV for kilomole of mixture as 76274 kilojoule per kilomole of mixture. This is the answer. Now let's go to our next bit. Here LHV kilojoule per meter cube mixture of mixture. Now that is equal to LHV kilojoule per kilomole of mixture into N by V, which is kilomole of mixture divided by MQ. Okay. So now here N by V can be found out from the ideal gas equation. Okay. So PV equal to NRUT from the ideal gas equation, then N by V equal to P by RUT, where P is our atmospheric pressure, which is 101.325 divided by 8.315 into 298, and the value comes out to be 0.0409 kilomole per meter cube. So the LHV kilojoule per meter cube of the mixture comes out to be 76274 into 0.0409, and the values of LHV meter cube per mixture comes out to be 3119 kilojoule per meter cube mixture. Now next question is 2.26. Okay, so the high heating value of the liquid octane C8H18 at 298 Kelvin is 47,893 kilojoule per kg, and the heat vaporization is 363 kilojoule per kg. Determine the enthalpy of formation at 298 Kelvin for a octane vapor. Okay. So now the things given is that here HHB higher heating value is at 298 Kelvin is C8H18 is equal to 47893 kilojoule per kg. Now HFG at 298 C8H18 is equal to 363 kilojoule per kg. Okay, to find HF naught bar at 298 C8H18 is equal to what? Assumption is complete combustion of C8H18 to form CO2, H2 and N2. All of the water in the products has condensed to liquid. No in dissociations. Okay. Now let's come to the solution part. By first law of thermodynamics, we know HR is equal to 298 is equal to HP plus 298 plus HHP 298 and C8H18 at steady state. Stoichiometric relation gives to C8H18 plus AO2 plus 3.76 AN2 gives rise to 8 CO2 plus 9 H2O liquid plus 3.76 AN2. Okay, and the value of A comes out to be x plus y by 4. What is x? X is 8 and y is 18 by 4. Okay, and the values comes out to be 12.5. Now HP at 298 Kelvin, we know the formula 8 into HF naught CO2 plus 9 into HF naught H2O minus HFG into H2O of liquid. Okay, so here the vapor minus the liquid is subtracted. Okay, this is the important turning point in this question, because these things are not covered initially, because this thing very twisting question is here. Okay, here you see the difference is taken of HF H naught F H2O and HFG. Why this thing is there, means why this difference is taken? Because in the question it's higher heating value instead of lower heating value, because most of the questions we see lower heating value, but in this question it is higher heating value. For higher heating value questions, you have to approach like this. You have to take the difference between the H naught F of the species. Okay, at vapor stage H naught F of the bar means in the molar basis. Okay, minus the HFG of H2O of liquid. Okay, you have to subtract this thing. That is the turning point in this question. Okay, when you substitute all this value, okay, and then plus 3.76 into A is 12.5 into H naught F of N2. Okay, because N2 nitrogen is naturally occurring state. Okay, in the atmosphere. Okay, so that's the reason why H naught F bar is 0 of N2. For N2 species it's 0. Okay, so now just substitute everything in this equation of HP, and then we can found the value of HP at 298 Kelvin as minus 5.7211 into 10 to the power 6 kilojoule per kilomole. Okay, so similarly we can find out the further reactants. Okay, so here HR of 298 it gives rise to H naught F C8H18 plus 12.5 H naught F of O2 and 3.76 12.5 into H naught F for N2. Okay, here bar I am ignoring because you know this is common, because bar is for the molar basis. That's it. Okay, not why I am telling, because not gives the significant of standard state. Okay, standard state condition. Okay, so now here you see for the O2 and N2 these values are 0 because these are occurring naturally in the atmosphere. Okay, so we only need to find out the H naught F plus for C8H18 of the liquid. Okay, now just substitute all the value in the our equation, that is HR of 298 gives rise to HP plus HHV. Okay, by substituting all these values you can get the value of H naught F C8H18 as minus 273 kilojoule per kilomole of fuel. Okay, so now we got the liquid but we need the vapor. Okay, so how you can do, yeah, for if one means I already saw this thing. If the thing is in vapor, then what thing is extra added, that is HFC is added. Okay, so what we will do, in the liquid state we just add the HFC to get the our vapor state enthalpy. Okay, the same thing is done here for the C8H18. Okay, just substitute the value and then get the value of H0F C8H18 of vapor as minus 208807 kilojoule per kilomole. Okay, okay, now the next question 27, find delta HR kilojoule per kg of the fuel. Okay, delta H add for kilojoule per kg of the mixture and delta air fuel ratio in mass basis. Okay, these are the things to be calculated. What are the things given? Given is that the following reaction: CH4 air, H2O2 and C of air. Okay, okay, given is the following reaction: CH4 air, H2O2 and C of air. Okay, to find delta H of delta HR kilojoule per kg of the fuel, delta HR kilojoule per kg of the mixture and air fuel ratio in mass basis. Okay, so now just proceed to our solution. Okay, now by first law of thermodynamics, delta HR is equal to NPHP minus NFHF minus NaHA. Okay, P is the product, F is the fuel, A is the air. Then for the A bit, methane air, CH4, we just write down the equation of the methane air combustion. CH4 plus AO2 plus 3.76 A and 2 gives rise to CO2 plus 2H2O plus 3.76 A and 2. Okay, so what is the A? A equal to x plus y by 4, which is equal to 1 plus 4 by 4, that is equal to 2. Okay, so now we have to find out the air fuel ratio for the methane. Okay, that is 4.76 A into molecular weight of the air and molecular weight of fuel, which is methane. Okay, and just substitute all the values: 4.76 into 2 into 28.85 in the divided by molecular weight of the methane, which is 16.043. Then the value comes out to be air fuel ratio of the fuel, which is 17.12. Okay, now just let's find out the delta HR bar. Okay, that is delta HR divided by NF. NF is per molecular per mole. It is calculated. Okay, we know the formula: summation of Ni by Nf into Hi of P minus Hf minus A by Nf H of O2 minus 3.76 Nf minus H of N2. Okay, basically here reactant for finding the delta H of the reaction, you have to just subtract from the product enthalpy from the reactant enthalpy. Okay, but yeah, so that's what the thing only done here. Okay, product minus reactant, this is the only thing done here for the finding enthalpy of the reaction. Okay, then just substitute all the values. Okay, product and reactant, everything all you just value just to substitute. Okay, just substitute the values, then we just get the value as minus 890,427 kilojoule per kilomole of fuel. Okay, so what is the thing, you have to just calculate kilojoule per kg of the fuel. So how you, what you do, just you just divide it by molecular weight of the fuel. Okay, and what is the fuel molecular weight? That is 16.043. Okay, by doing all this thing you just get as minus 55,555,503 kilojoule per kg of the fuel. But the nothing is, we need to take the value of kilojoule per kg of the mixture. Then how you will calculate? You have to just multiply kilojoule per kg of the fuel into 1 by 1 plus air fuel ratio. Okay, and the unit is kg of the fuel, and the kg of the fuel just cancelled in the units. Okay, and the final value of the final unit should be kilojoule per kg of the mixture, and the value should be minus 30663 kilojoule per kg of the mixture. Okay, so now delta H of the reaction, delta H just find out. Okay, similarly, if there is one other reaction like H2O2 reaction will be there, that is H2 plus AO2 gives us to H2O liquid. Okay, so what is A equal to X plus Y by 4. Here there is no carbon species, so that is 2 by 4, that is 1 by 2. Okay, what is air fuel ratio? Air fuel ratio A into molecular weight of the fuel divided by molecular weight of the H2. Okay, just substitute the values and get the air fuel ratio, which is equal to 8. Okay, similar as the previous question, you just have to find out the delta H R, which is equal to H of H2 of the liquid minus 1 by 2 H of O2 minus H of H2. Okay, because here O2 and H2 are both are in naturally occurring element, so the enthalpy are 0. So the final enthalpy should be minus 285,856 kilojoule per kilomole of fuel. Okay, so now now the thing is, we have to find out delta HR kilojoule per kg of the mixture. Okay, so for that we have to find out first kilojoule per kg of the fuel, then we have to find out convert it to kilojoule per kg of the mixture. Same way, we just have to multiply 1 by divided by molecular weight of the fuel, and we just get the value of delta HR minus 142,928 kilojoule per kg of the fuel. And similar as the previous procedure, you just also have to multiply with 1 by 1 plus air fuel ratio. Okay, with the delta HR kilojoule per kg of the fuel, then you just get the value as 15880 kilojoule per kg of the mixture. Okay, then one more reaction, carbon and air reaction, that is C at the solid state AO2 plus 3.76 AN2, means carbon and air reaction gives rise to CO2 and N2. Okay, here A equal to, here there is only carbon is there, but there is no hydrogen, so the A equal to 1. So the substitute and find out the value of air fuel ratio in mass basis, which gives rise to 11.44. Now when you substitute in delta H bar of R, okay, delta H reaction, okay, you see for N2 carbon and oxygen, this value of delta H enthalpy will be 0 because they are occurring naturally. Only for CO2 you just have the value, that is minus 393,456, because only one CO2 is there, so 1 we just multiply, then the value comes out to be minus 393,546 kilojoule per kilomole of mixture, sorry, fuel, kilojoule per kilomole of fuel. Now we have to find out the kilojoule per kg of the fuel. What you have to do, you have to just divide it by molecular weight of the fuel. Okay, the same procedure we just follow, and the final value is minus 32796 kg per kilojoule per kg of the fuel. Okay, so similar way also, for finding kilojoule per kg of the mixture, you just have to multiply with 1 by 1 plus air fuel ratio, and the values comes out to be kilojoule per kg of the mixture. Okay, and the final value comes out to be minus 2636 kilojoule per kg of the mixture. Okay, now it's chapter 4. Previous one is chapter 2, now it's chapter 4. Okay, and the question is, The NO formation mechanism is called the extended Zeldovich mechanism. O plus N2 gives rise to NO plus N. Okay, this is K1F is the constant they just given. Okay, so similarly N plus O2 gives rise to NO plus O, and N plus OH gives rise to NO plus OH. Okay, with assumption of equilibrium concentration O, O2, N2, H and OH applied this three-step mechanism, find the expression for the steady state nitrogen atom concentration, neglecting the reverse reactions, the NO formation rate. Okay, DNO of dt. Okay, so here only forward reaction rates constants are given and forward reactions are given. Okay, there is no reverse reaction. Okay, and you have to find out the DNO of dt. Okay, same thing I just write down as given. Okay, to find steady state nitrogen atom concentration expression, and the expression for NO formation rate dNO by dt. Okay, let's proceed to the solution. dN by dt equal to K1F ON2 minus K2F NO2 K3F NO4H equal to 0 at steady state. Therefrom you can calculate the nitrogen atom concentration. Okay, K1F O into N2 divided by K2F O2 plus K3F OH. Okay, similarly you can find out d of n dNO by dt, which is equal to K1F ON2 plus K2F NO2 K3F NOH. Okay, and the values comes out to be, you substitute all those values. Okay, then your final expression of dNO by dt equal to 2K1F O2 O plus O into N2. Okay, so this is our final answer. Okay, let's just see the steps how it's done. Okay, the next question. Okay, now question number 4.18. Consider the following CO oxidation reaction. CO plus OH gives rise to CO2 plus H. CO plus O2 gives rise to CO2 plus O. And K1 and K2 as the reaction rate constants. Okay. What is the unit of reaction rate constant? That is centimeter of Q plus per gram mole second. It's in CGS unit. You can convert it to SI unit, which is meter cube per kilomole second. Okay. So some values are given and some expression is also given. Okay. RU also given. Okay. So calculate and compare the characteristics time associated with these two reactions for T equal to 2000 Kelvin and P equal to 180. The CO mole fraction is 0.011 and OH and O2 mole fractions are 3.68 10 to the power 3 and 6.43 10 to the power 3 respectively. Okay. Some things are given. Okay, we see the first the reaction. Okay, we just write down what are the things given. Okay, the reaction is COOH, this reaction here, K1 expression and K2 expression we just write down. T given, pressure given, X of CO, X of OH and X of O2 given. Okay, so to find tau chem is the characteristics time for two CO reactions and compare. Okay, so you know very well we have to do some assumptions, right? Here X of CO will be very greater than X of OH. Okay, and X of CO and very bigger than the X of O2. Okay, so what we will do, we just find out the CO concentration as X of CO equal to P by RUT. Okay, and just find out the value of CO. Then numerically evaluating K1 and K2. K1 we just know the value, that is 1.17 10 to the power 7, 2000 to the power 1.35, exponential of 3000 divided by 8.315 divided by 2000. Okay, we just find out the value as K1 equal to 4.008 into 10 to the power 11 centimeter cube divided by gram mole second. Okay, and K2 equal to 2.5 into 10 to the power 12 exponential of minus what 20 lakhs I think, or not 20 lakhs, I think 2 lakhs. Yeah, 2 lakhs. Yeah, 2 lakhs. 2 lakhs divided by 8.315 into 2000. Okay, and the value of K2 comes out to be 1.496 into 10 to the power 7 centimeter cube per gram mole second. Okay, so you just got the K1 and K2. Okay, now we just know the formula of tau chem. Tau chem the characteristic time ln E plus 1 minus E A naught divided by B naught divided by B naught minus A naught into K of bimolecule. Bimolecule means it's a bimolecular reaction. Their characteristic time constant. Okay, don't confuse it K1 and K2. K1, K2 and K bimolecule are absolutely same. Okay, so here CO is very I already told this assumption. Okay, from this assumption we can just cut some terms. Okay, and we can make it as, because we know if B naught is very greater than A naught, then the tau chem reduces to 1 by B naught into K bimolecule. Okay, so similar the same assumption we already know, I already told, and same thing we just applied, so that this bigger expression can be reduces to, for the K1, that is tau chem K1, it gives rise to 1 by CO K1. Okay, 1 divided by CO K1. Okay, CO concentration you already know, and K1 also now you just find out. Okay, now you find out the tau chem K1, which is gives rise to 3.72 into 10 to the power minus 5 second. Okay, similarly you can find out the tau chem of for K2, which is equal to 1 divided by CO into K2. Okay, and the values comes out to be 0.997 second. Okay, all these units should be in second. Okay, let's come to some third questions. Okay, the terms accounting for turbulence effects contain Reynolds stresses, turbulent kinetic energy, dissipation of the turbulent kinetic energy, and length scale terms. Okay, you just read it, this thing. Okay, Now you see the turbulent stresses gives rise to two terms. Okay, one is divergence of rho v vector u prime and j prime whole bar, and rho ui prime and uj prime. Okay, so the first term is the turbulent transport of kinetic energy by means of Reynolds stress. Okay, and the second term is net decrease in kinetic energy due to the deformation of work by Reynolds stress. Okay, this both the terms contains the Reynolds stress. Okay, so the terms accounting for the turbulence effect contains a Reynolds stress. Okay, if there will be turbulence, then there will be a Reynolds stress for sure. Okay, that is what the question. And also I show you two types of Reynolds stress. Okay. In high Reynolds number turbulent flows, dash terms dominate. Okay, if there is a high Reynolds number turbulent flow is there. Okay, so the answer should be turbulent effect terms. Okay, there is lots of term will be there, but means most of the wrong answers should be viscous terms. Okay, because mostly we tell that the viscous term should dominate, but that is absolutely wrong, because the high Reynolds number turbulent flow, the difference between the length scales will be very large. Okay, and the large eddies are more energetic. If there is a large eddy is there, that eddies are very more energetics. Okay, so for high Reynolds number flow, turbulent effect is more significant than the viscous effect. Okay, so in high Reynolds number turbulent flow, the turbulent effect term is very dominant. Okay, which is D option. Okay, express the large scale velocity in terms of k and epsilon. Okay, so the it's very simple question and it's a basic question. Directly you can know that velocity scale of the large eddies or the large scale velocity are the both are same thing, which is equal to k to the power 1 by 2. And what is k? K is the turbulent kinetic energy. Okay, so answer is C. Express the large scale length in terms of k and epsilon. Okay, the length scale of the large eddies or the large scale length both are same term, which is equal to k to the power 3 by 2 divided by epsilon, where k is the turbulent kinetic energy and epsilon is the dissipation rate or turbulent dissipation rate. Next question. Let Cm be the dimensionless constant and rho be the density of the flow. Express the eddy dynamic viscosity in terms of k and epsilon. Okay. The answer should be A, that is rho C mu k square by epsilon. And how is it? You see, eddy dynamic viscosity equal to C mu into rho VL. What is C mu? C mu is the dimensionless constant. V is the velocity scale of large eddies. Okay, rho is the density of the flow, and L is the length scale of the large eddies. Okay, eddy dynamic viscosity mu t also called as turbulent dynamic viscosity, and you know the value is just C mu into rho into k square by epsilon. Okay, and C mu is adjustable dimensionless constant, and the values are always 0.09. We mostly take this value. Okay, but it can be changed depending upon the situation and the conditions of the flow, turbulent flow. So for the molecular, next question, for the molecular diffusion of the liquid, the diffusing molecules having criteria of steady state diffusion of B over a non-diffusing A, then n flux of A is what? The answer is B, which is 0. That is steady state diffusion of B is equal to over non-diffusing A is equal to n flux of A, because the thing is, if there is if somebody in steady state, okay, and it's also non-diffusing. If something is non-diffusing and in steady state, there is no effect. If somebody is non-diffusing, okay, here A is non-diffusing, so there is no effect. If there is no effect on the diffusion, then there will be no flux of A. Okay, so the n flux equal to 0. For the liquid molecular diffusion of A and B, the steady state equimolar counter diffusion, the n flux of A is negative of n flux of B. Okay, is it true or false? Is obviously it's a true statement. The equimolar counter diffusion, in case of EQ, this is the condition that for only equimolar counter diffusion, this condition will apply, that is n flux of A equal to minus of n flux of B. Okay. Find the change in concentration for a steady state equimolar counter diffusion if DAV equal to 6 square meter second or meter square second, the change in distance is 2 meter and influx of air is equal to 5 mole per meter square second. So this is a problematic question. Okay, here you know very well influx of A equal to d of AB divided by Z into concentration difference. Okay, what is d of AB? Steady state equimolar counter diffusion. Okay, and Z is the change in distance. Okay, when you substitute all these values, we just get the concentration difference as 5 by 3, which is 1.67. Find the diffusivity of AB in square meter square second if influx of A is 5 mole per meter square second, concentration difference is 2 cube per meter 2 mole per meter cube. Okay, and distance is 3 meter. When you because we know already the formula, influx of A is equal to d of AB divided by Z into concentration difference. Okay, just substitute the value and then get the value of DAB, which comes out to be 7.5 meter square second. Okay, so we just solve some of the problems from the last lecture number 12, also some important questions also. Okay, then we end the section. Okay, estimate the mass burning rate of a 1 mm diameter N-hexane droplet burning in air at atmospheric pressure, assuming no heat is conducted into the interior of the liquid droplet and that the droplet temperature is equal to the boiling temperature. The ambient air is at 298 Kelvin. Okay, you have to solve this question. I think most probably this is the last question. What are the things given? A 1 mm diameter Okay, here given a 1 mm diameter N-hexane droplet burning in air at 298 Kelvin and 1 atmospheric pressure. The droplet temperature is equal to the hexane boiling point. Okay, what we need to find out? The mass burning rate m dot f. Okay. Okay, what are the assumptions? Quasi steady spherical symmetric droplet. Okay, what are the assumptions? Quasi steady spherical symmetric droplet combustion model applies. Okay, let's go to the solution part. M dot F equal to 4 pi kg into RS divided by CPG ln of 1 plus BOQ. Sorry, BOQ delta SC by nu plus CPG T infinity minus TS divided by QIL. Okay, plus HFG. Okay, QIL equal to 0 because there is no heat into interior. Because it's not given, so we assume it as 0. Properties. T var is equal to 1 by 2 TF plus TS. Gas. TF is equal to, let it be 2000 Kelvin. Then TS equal to T boil equal to 342.1 Kelvin, which is table B.1. Okay. What is the T bar? T bar is equal to 1 by 2 2000 plus 342.1 1271 Kelvin. CPG equal to CP of hexane 1271. Okay, the values comes out to be 4390 joule per kg Kelvin. We taken this value from table B.2. Okay. Okay, kf equal to k hexane at 1271 Kelvin. Okay, this value is beyond curve fit limits of table B.3. You have to see all this table in our book, prescribed textbook. Okay, SR Turn, An Introduction to Combustion, 3rd edition, McGill 2017. Okay, so approximate as ideal gas. K2 is equal to K1 into T2 by T1 to the power 1 by 2. Equation 3.27. Okay, at 1000 Kelvin, table B.3 yields K is equal to 0.13525. Next is Kf is equal to 0.13525 divided by 1000 to the power 1 by 2. The values comes out to be 0.1525 watt per meter Kelvin. K infinity is equal to K of air is equal to 0.08347 watt per meter Kelvin. Table C.1. Okay, Kg is equal to 0.4 Kf into Kg. 1525 all this value is just taken from table B.1. A stoichiometric ratio nu is equal to 4.76 times A molecular rate of air divided by molecular rate of the fuel, okay, which is equal to 4.766 plus 14 by 4 28.85 divided by 86.177. This value comes out to be 15.14 kg of air by kg of fuel, okay. Next is our B of OQ, which is equal to 45101 divided by 15.14 plus 4390298 minus 342.1 divided by 33,500. Okay. Then by solving we just get the value of BOQ as 8.3144. Substitute in m dot f the value of BOQ, then find out the value of m dot f, which is our answer. M dot f equal to 4 pi 0.111 0. Triple 05 4390 ln of 8.3144 plus 1. M dot f 3.93 10 to the power minus 7 kg per second. Okay. Okay. With this we can end the section or summary section. Okay. Whatever the most important questions I just solved. Okay. Still you have to solve the question from the books. Okay. That is I already tell the prescribed textbook. An Introduction to Combustion, McGrill, third edition by a certain author. Okay, author name is a certain. Okay, so and you have to also see some of the objective questions in www.sunfoundry.com also. Okay, so you go through all these things. Okay, okay, go thoroughly to the also lecture notes, and also my live discussion sections also. Okay, if there is any doubt, any kind of doubt you have related to our subject, okay, our syllabus, you can ask me in this channel. Okay, for this for particular lecture you can ask in this comment section. Okay, and for other lectures you can also ask in their respective comment sections in my YouTube channel, that is Sumit Sagar Hota. Okay, you already know also, this is the YouTube channel link. Okay, okay, if you already know, that's very good. Okay, I upload all the videos here also. Okay, you can watch all these things, and if you have any doubt you can ask in the respective comment sections. And how much maximum question possible I will also solved in this for this syllabus. If there is any question left, you can also ask me those questions also. Okay, I will most probably I will answer all the questions whatever you have doubts. Okay, and all the best for your exam. And I think the exam will be, I think, 23 or something. Okay, all the best for that exam. With this we end the whole section of the course Turbulent Combustion, Theory and Modeling by Professor Ashok Desai. All the live discussion section and summary sections. Thank you very much for attending this section. Keep learning, and if there is any doubt, you can ask me. Happy learning and good night.